topic is variable electrovalency. What do we understand by electrovalency? Electrovalency हमने पिछली वाली क्लास में पढ़ा था. When a bond is formed by transfer of electrons, then that is known as what? Electrovalency, right? And electrovalency of every element, that is going to be what? It is going to be the number of electrons in the outermost shell. That is what we had studied in the previous class. Okay. Then what is this new term which we are doing now? Variable electrovalency. Variable means different. There are many metals which show variable electrovalency. Like for example, if you are talking of transition metals, let's say we are talking of transition metals, and let's take the examples of few. Like if we are taking Fe2 positive and Fe3 positive, then what are we saying? That iron is showing two different valencies. One is Fe2 positive and the other one, that is Fe3 positive, right? Similarly, we can also say that nickel shows Ni2 positive and Ni3 positive. Okay, Fe2 positive, that is known as the ferrous ion, and Fe3 positive, that is known as the ferric ion. So the smaller oxidation number, that is going to be Us, and the higher oxidation number, that is going to be Ik. Similarly, this is known as nickelous and this is known as nickel. Okay, so transition metals specifically, almost all of them show variable electrovalency. What can be the reason behind this? The reason is, the first reason, that is the instability of the core. What do we understand by the word core over here? Core means that when we have taken out or we have removed one electron from the valence shell, the residual configuration, that is known as core. Okay, so we are saying कि on removal of an electron from the metal, the residual configuration which is left behind, that is known as the core. So if the core is going to be unstable, it is has a tendency to lose more electrons to come to a stable electronic configuration. For example, let's take the example of these two ions which we have taken over here. We are taking iron atom, right, with atomic number of 26, and the electronic configuration, that is going to be argon 4s2 3d6. Right. Now, if iron is losing 2 electrons, Fe2 positive, the atomic number now becomes equal to 24, and the electronic configuration, that will become as 4s0 3d6. Right? Now we know that 3d6 is not a stable configuration, but 3d5 is going to be a stable configuration. So half filled and fully filled, they have extra stability. Na? So in order to come to, this is known as an unstable core. Right? In order to attain a stable core, Fe2 positive loses one more electron to go into Fe3 positive state with 20. How many electrons? Sorry. 24 and 23 electrons. Okay. So if we are going to 23, we have argon 4s0 3d5. Now this gives it a stable configuration. Therefore we say that Fe3 positive, that is going to be more stable with respect to Fe2 positive. So if we have two different compounds of iron, one is FeCl2 and the other one, that is FeCl3, then the stability of FeCl3, that is going to be greater than the stability of FeCl2. Is it clear? Similarly, if we want to see something else, let's take the example of nickel. Nickel has how many? 28. Atomic number of nickel, that is going to be 28. so electronic configuration is argon 4s2 3d8. Right? Now if we look at the electronic configuration of Ni2 positive, this is going to be argon 4s0 3d8. Right? Now in case of 3d8, we see that if we are looking at the orbital picture of 3d8, then we have 5 orbitals, and 3d8 means 1, 2, 3, 4, 5, 6, 7 and 8. There are 2 unpaired electrons over here. Then if we are going to Ni3 positive, the electronic configuration now becomes argon 4s0 3d7. Right? So if we're looking at the orbital picture over here, so we have 1, 2, 3, 4, 5, 6 and 7. You can see 3 unpaired electrons. Therefore, in this case, Ni3 positive, that is going to be more reactive with respect to Ni2 positive. Right? So the compounds of Ni2 positive are more stable as compared to compounds of Ni3 positive. So this is the reason which we give to variable oxidation states. Another reason which we can give, that is inert pair effect. Inert pair effect. This effect is more prevalent or more predominant in the p block. Okay, when we are going to the higher or the heavier metals or the heavier members of the p block, they show variable oxidation states due to inert pair effect. What is inert pair effect? Inert pair effect is the reluctance of s orbitals to participate in bonding. Okay, it is the reluctance of s orbitals to participate in bonding, which means that if we are looking at, say, the electronic configuration of some higher element, say Sn, okay, Sn that belongs to group 14. If you are looking at the general electronic configuration of tin, the general electronic configuration is going to be Ns2Np2. Right? Now over here in group 14, the valence electrons, they are 4. So tin can either lose all 4 electrons or it can lose only 2 electrons. So it has 2 oxidation states. One is when it is losing only 2 electrons, then the oxidation state is Sn2 positive. When it is losing 4 electrons, the oxidation state is Sn4 positive. Okay? So over here we say that as we keep going down the group, so if you're looking at carbon, silicon, germanium, tin and lead, as we keep going down the group, the lower oxidation state keeps on becoming more stable. Okay, so Sn4 or Sn2, if we are comparing, then Sn4 is more stable, but if we go to lead will also show the same oxidation states, Pb2 positive and Pb4 positive. Okay? So यहाँ पे Pb2 positive is going to be more stable than Pb4 positive, but in this case Sn4 is more positive than Sn2 positive. Right? So as we keep going down the group, due to higher penetration effect, the s electrons, they do not participate in bonding, as a result of which lead will only lose these 2 electrons to give us a stable configuration of Pb2 positive. Now these, we will also study further that these kind of variable oxidation states categorizes the p block into oxidizing and reducing agents. Okay? Anything which has a tendency to lose electrons, that is going to behave as a reducing agent. And anything which has a tendency to gain electrons, that is going to behave as an oxidizing agent. Okay? So So if we're comparing both of these, the stable electronic configuration over here for tin, that is 4 positive. Okay, so it is going from 2 positive to 4 positive, that is it is losing, it has a tendency to lose electrons. So all the compounds of tin in +4 oxidation state, they are going to become good reducing agents. Okay? Similarly, when we are talking of lead has a tendency to gain electrons because Pb2 positive is a stable oxidation state. So it is going to behave as a good oxidizing agent. Right? When we do we will do the S and P block, then we will study this in greater detail. But right now you should only know that inert pair effect is the reluctance of s orbitals to participate in bonding. Another example we can take is that of group 15. If we're talking of group 15 over here, the electronic configuration is NS2, NP, 3, group 15, right? 5 valence electrons, but as we keep going down the group consists of nitrogen, phosphorus, arsenic, antimony and bismuth. So in case of bismuth, Bi3 positive state is going to be more stable than Bi5 positive, because it will give us a variable valency of 3 positive and 5 positive. Okay? So this is what inert pair effect is. Clear? Okay. फिर उसके बाद we go on to the second kind of bond today, that is known as the covalent bond. The second type of bond, that is known as the covalent bond. Covalent bond is formed by mutual sharing of electrons. It is formed by mutual sharing of electrons, right? This covalent bond concept that was proposed by Lewis in the year 1916. Okay, now over here, according to this concept, there are certain atoms which do not have the tendency to gain or lose electrons. So rather than gaining or losing electrons, they tend to share the electrons. That is going to form a covalent bond, right? Now in this case you need to remember that there is no charge on the atom. Why? Because both the atoms are equally contributing towards the formation of a bond. So neither do they completely lose the electrons, nor do they completely gain the electrons. So that is why when we were studying the electrovalent bond, we studied that there is going to be positive charge if the atom is losing electron to form a cation, or there is going to be a negative charge if it is gaining electrons to form an anion. Nothing of this sort is going to happen over here, right? So if we are defining a covalent bond, what is a covalent bond? It is formed by mutual sharing of electrons contributed by each atom. Okay? Contributed by each atom. What are the conditions for formation of covalent bonds? The first condition is similar electronegativity. Similar electronegativity. Both the elements, they they should have similar electronegativity such that we say that the bond formation which is taking over here, in that the shared pair of electrons remains in the center. Okay, there should be the electronegativity difference should be 0. Okay, now such a bond which is formed due to 0 electronegativity difference between the both elements, that is known as a non-polar covalent bond, right? As in the case of hydrogen. As in the case of hydrogen. Right? Now over here, mostly the non-polar bond that is formed in between similar kind of atoms. Right? It is formed in between similar kind of atoms. Okay, so that is what a non-polar bond is. Or in other words, you can say that this kind of bond that is formed in between homogeneous molecules, that is molecules having same kind of atoms. Yeah, homoatomic molecules also you can write down, homoatomic molecules. Right? Now we say the second reason is that we know that bond formation will take place in order to attain a stable octet rule. This we have already studied. In order to attain the nearest noble gas configuration, the atoms they get bound to or they get bound to each other. Now if there are atoms which are short of electrons, than their noble gas configuration, then they try to share the electrons with other atoms to form a bond. So these are the two conditions for the formation of covalent bonds. Let's take a few examples. We have taken one oxygen. When only one electron pair is sharing over here, then this is known as a single bond represented by a single line. Okay? If you're looking at oxygen has 6 electrons in the outermost shell. So another oxygen will also have 6 electrons in the outermost shell. It needs 2 more electrons to complete its octet, right? So this oxygen is going to share the electrons of this one and here. So we can see that there is 2 electrons shared between both the oxygens, so this gives us a double bond, right? Similarly, if you're talking of nitrogen has 5 electrons. Right? So you can see that 3 electron pairs are being shared over here. So nitrogen is giving us a triple bond. Okay. Now in case of oxygen, you can see that these 2 electrons they are participating in bonding, but both the pairs they are not participating in bonding. So the ones which are not participating in bonding, they can be written as this. They can be represented by dots. Okay. Similarly, when we are talking of nitrogen over here, we can see that these 2 electron pairs they are not participating in bonding, so they can also be represented by 2 dots. Okay. So there are 2 types of electron pairs which are present in the covalent bond. The one which are participating in bonding, they are known as bonded electrons. ठीक है? Whereas the other one which is not participating in bonding, they are known as lone pair of electrons. So you need to remember this because this terminology we will use again and again. ठीक है? So जो participate कर रहे हैं bonding में उनको आप बुला रहे हैं bonded electrons और जो participate नहीं कर रहे हैं उनको हम क्या बुला रहे हैं? They are known as lone pair of electrons. Right? So this is what covalent bond is. These structures which we have drawn over here, these are known as Lewis-George structures. We will do this section also in detail in the coming classes. Right? So let's go on to what do we understand by covalency. What do we understand by covalency? Covalency is the number of electrons contributed by an atom right towards formation of a covalent bond. So it is the number of electrons contributed by an atom towards formation of a covalent bond. Right? So we generally, what do we say? That the S and P electrons of the valence shell, they participate in bonding. And that gives us the covalency. Like for example, if we have hydrogen, right? We know that the electronic configuration of hydrogen is 1s1. So what is going to be the covalency over here? The covalency will be 1. Similarly, if we are talking of fluorine, fluorine has the electronic configuration of 2s2, 2p5. Okay, it has electronic configuration of 2s2, 2p5. Now over here you can see that these three orbitals, they have paired electrons. There is only one orbital which has one single unpaired electron. So this unpaired electron will only be shared. Hence the covalency over here also becomes 1. Right? The paired electrons, they do not participate in bonding. Only the unpaired electrons will participate in bonding. ठीक है? उसी तरह से we have oxygen, electronic configuration 2s2, 2p4. Right? So over here you can see that there are two unpaired electrons. Therefore, the covalency of oxygen, that is going to be 2. Right? So this is how we find out the covalency of the atoms. Right? Now, what are we saying over here is, if there are elements which have vacant d orbitals, they may have variable valencies. Right? If there are vacant d orbitals present, then the electrons get excited into the d orbital and hence they become unpaired. Like, let's take the example of phosphorus over here. Phosphorus, the electronic configuration is 3s, 2, 3p3, and it also has 5 vacant orbitals of 3d. ठीक है? अब ये क्या है? This is the ground state electronic configuration of phosphorus. According to the ground state electronic configuration, the atom of phosphorus can only show 3 covalency. But it is seen that phosphorus shows a covalency of 5. That can be explained on the fact that phosphorus, before going into bonding, goes to an excited state in which one of the electron from S gets excited to 3d, such that the electronic configuration will now become right? So you can see over here that there are 5 unpaired electrons, as a result of which phosphorus can show a covalency of 5 because of 5 unpaired electrons, right? Similarly, all the second members of each group, they can exhibit this kind of a behavior, right? Like if we are saying that we're talking of fluorine. Fluorine is the first member of its group. It does not have vacant d orbitals, so it cannot extend its valency than 1. But chlorine, due to presence of vacant d orbitals, let's take the molecule of chlorine over here. Chlorine, in the ground state, the electronic configuration is going to be 3s, 3p, and 3d. Okay, so this is 3s, 3p, 3d. Here there is only one paired electron present. So in the ground state, the valency or the covalency of chlorine is going to be only 1. But if it goes to excited state, then all these electrons, they can be unpaired. We have again 3s, we have 3p, and we have 3d. Okay, na? So here there is going to be one electron. From here one electron goes over here. यहाँ पे भी एक electron. From here one electron goes over here. यहाँ पे भी एक electron. So now you can see 1, 2, 3, 4, 5, 6, 7. So chlorine can extend its covalency to 7. It shows a covalency of 1. It shows that of 2, 3, 4, 5, 6 and 7. Right? For example, in the compound of Cl2O7, the oxidation state of chlorine is 7. Okay? Is it clear? So this is what covalency means. Then what do we understand by covalent compounds? What are covalent compounds? What are covalent compounds? Covalent compounds are those in which covalent bonds are present, right? And covalent bonds, they are formed by mutual sharing of electrons. Let's go on to the characteristics of covalent compounds. The first one, that is physical state. As we have discussed that the ionic compounds, they mostly exist as solids because the forces of attraction in case of covalent compounds are weak, right? As a result of which these exist as gases or liquids due to weak forces of attraction. Okay? Due to weak forces of attraction, and they also have low boiling points. Right? Then second property, let's elaborate this point from here. Low melting points and boiling points. The reason I have already given that they have low melting and boiling points due to weak forces of attraction, except for certain covalent compounds like silicon carbide, which is known as carborundum, then diamond, then silica. These have, silica is SiO2. These have higher melting points because of their giant molecules, or we can say that these have three-dimensional network structures, as a result of which the forces of attraction, they become stronger and they have higher melting points. Okay? The next is we have third. Some of the covalent compounds, they exhibit crystal structure. These crystal structures, they are of three types. Okay? The first one that is known as, we say that the units in this case are molecules. First type of covalent crystal structure is in which the units, they are molecules, and the molecules, they are held together by weak van der Waals forces. Okay? They are held together by weak van der Waals forces. Examples are sulfur, iodine, phosphorus, etc. These are few examples of the first type of crystal structures which are present. The second type crystals have lattice layers. In the second type of crystal structure, there are present lattice layers. Right? For example, graphite. Because of the layered structure of graphite, it has one free electron and thus it conducts electricity. Okay? And also, due to its layer structure, one layer can slide over other. One layer can slide over other. That is the reason why it marks paper black. Okay? And also due to the structure of graphite, it is very soft, as a result of which it is used as a lubricant. Right? Then the third type is in which every atom is bonded to 4 other atoms. So basically over here the units, they are going to be atoms having a 3-dimensional structure. As for example, we can say diamond. Even for that matter, silicon carbide also is an example. Silicon carbide, aluminium nitride, right? So these crystals, they are going to be very hard. They are very hard and have high melting points. Very high melting points. Okay? So these are the 3 type of crystal structures which the covalent bonds have. Then the next we come to the next property, which is electrical conductivity. Electrical conductivity. Okay, now electrical conductivity, when we are talking of, we say that the covalent compounds, they are bad conductors. They do not conduct electricity because they do not have free electrons or they do not have free ions. Okay, but there are certain polar covalent compounds about which we will study in our next topic, polar covalent compounds which have free ions. What are polar covalent compounds? As for example, we are taking HCl. Over here chlorine is more electronegative than hydrogen, so it is going to attract the shared pair of electrons towards itself, which gives a slight negative charge to chlorine and slight positive charge to hydrogen. Right? So such compounds, although sharing of electrons is taking place over here, but still one of the electron or the electron pair that is attracted more towards the more electronegative atom, which gives it a slight negative charge. So such compounds, they can conduct electricity in the solution states. Okay? Clear ho gaya? So these are electrical conductivity. Then fifth is solubility. These compounds are insoluble in water, right, except for polar compounds, except for polar covalent compounds. Okay? And they are soluble in organic solvents, like ether, carbon tetrachloride, benzene, etc. ठीक है? Clear हो गया? Then why this is happening? This is due to the principle like dissolves like. Due to the principle like dissolves like. ठीक है? Then sixth is that almost all covalent compounds, they undergo molecular reactions. Okay? They undergo molecular reactions. Because of these molecular reactions, the reactions of covalent compounds is very slow. Right? So, the kinetics of these compounds, that is going to be slow. Then the next property is isomerism. We have already studied about this, that the covalent compounds, they are rigid and directional. Okay? These compounds, they are rigid and directional. Because of their directional nature, they show different structures in space. So, you know what isomerism is? Isomerism is those compounds having the same molecular formula but different structural formula, they are said to be isomers, and the process is known as isomerism. So they exhibit isomerism, right? Both structural and space. So this is all about the covalent compounds. Now we've done two kinds of compounds. Let's do the differences between them. We have ionic compounds and we have covalent compounds. Ionic compounds and covalent compounds. The first difference is that the ionic compounds, they exist as crystalline solids at room temperature, right? Whereas covalent compounds, they exist as liquids or gases at room temperature. Okay? Then the ionic compounds, they are hard and brittle, whereas the covalent compounds, they are soft and waxy, except for the large compounds like diaminonol, which examples we did just now. So otherwise, the these compounds, if they exist as solids, they are soft and waxy. ठीक है? Then number 3, the ionic compounds, they have high melting and boiling points. ठीक है? Whereas covalent compounds have low melting and boiling points. They have low melting and boiling points. ठीक है? फिर number 4, they are soluble in water. And these are soluble in organic solvents. These are soluble in organic solvents. ठीक है? फिर उसके बाद these are good conductors of electricity. In molten or aqueous state. ठीक है? Whereas covalent compounds are bad conductors. ठीक है जी? Then number 6, the ionic compounds undergo ionic reactions. Whereas the covalent compounds undergo molecular reactions. So the reactions of ionic compounds are instantaneous, they are very very fast, whereas those of covalent compounds, they are slow reactions. ठीक है? So today we will do only till here.